Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am very happy to have Immanuel Jebaraj with us today. Hello, Immanuel.
Hello, Frank. How are you?
I am doing awesome on this November 18th of 2024 as we record this. And I am in Phoenix and we are cooling down a little bit, which is really nice because otherwise we're very hot. So we're entering a very lovely part of the year. And Emmanuel, what's your geolocation? Where are you at?
I'm in Finland here. Speaking of cooling down,
Yeah.
we're gonna get a snowstorm later this week, so looking forward to that.
Okay.
Gotta go to work outside.
So have you seen the Aurora Borealis?
Um, in May, yes, during
Yeah,
the
cool.
superstorms, we
Cool.
could see it just from our apartment. Actually, it was great. We even took a little stroll by the road, and there's so many people looking at it. It's
Yeah.
amazing. Yeah,
That's
it's an
still on my
experience.
bid bucket. I still have never seen one, so it's on my bid bucket.
Wow,
Oh,
I'm
maybe I'll
actually
come and
surprised.
visit you in Finland. How about that?
That would be great, actually. I thought Arizona would have been able to see it, considering you got so many deserts there. So
Yeah, but we're
it's a
really
huge
close.
desert.
It's going to take a pretty big storm for us to be able.
Okay. Well,
So,
hopefully
but I've
one
been
day.
looking. I've been looking. No, no, no. So, very cool. Very cool. And what's your position there in Finland?
I'm a postdoctoral researcher at the moment. I completed my PhD very recently in 2021, late 2021. Thank you. So I did that in Belgium, and then I moved to Finland in Turku. It's quite close. It's not such a big move, but I really enjoyed here.
Very cool. Very nice. And Emmanuel, what do you like to do for research?
My research interests have been so I did quite a lot of fundamental plasma physics with radio in particular. So along the radio wavelength, so it's to study the emission processes and also the source of these radio emissions. But now I've kind of diverged a little bit from there. I do a bit more about the source themselves. So, for instance, shock waves and also flares on the sun. So these things kind of manifest themselves in the radio wavelengths, and I kind of have 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 enjoyed doing this quite a bit more. And so with our team here, I think we found a very good balance of like experimentalists and theorists. So
Yeah, yeah.
yeah, so these are my research interests for now. So we have
Very
to see
cool.
how it evolves.
Very cool. And that is going to bring us to this very awesome APJ letter. It is open access. It's the open access era. People go grab a copy for free. Go get one. Direct measurements of synchrotron emitting electrons at near sun shocks. And Emmanuel, take us away.
It sounds much better when you read it. Yeah,
Yeah.
so so as the title says, it's the direct measurements of the synchrotron emissions, which are quite rare in near-sun shocks. And this work was done with quite a lot of people there, as you will notice. Quite a lot. I would like to give a huge shout out to all the instrumentation people on which have put together the Parker Solar Probe, for instance,
Oh,
an
yeah.
amazing spacecraft. Um, yeah, exactly. So this study is 100% Parker Solar Probe. So that's why you see quite a lot of the instrumentation experts in there. And without them, I have to say none of this would have been possible. So
Indeed.
and of course all my other collaborators as well. I really enjoyed it was a fun study, I have to say. It's one of those things, like it's like start to end, just amazing discussions and fun to do stuff.
Nice. Very nice. Beautiful shout out. Okay, let's go ahead and get into the Parker Solar Probe stuff. Here we go.
um so this study is unique in a way. It's placed in the right spot because let's think about for an instance, because astrophysics has been a subject where people have been really interested in for instance.
Yes.
So you have things like supernova remnants. The supernova remnants, the thing about supernova remnants is that they're beautiful. You can see them from very far away,
Yes.
uh, but there's no way of knowing how exactly these shocks evolve. So supernova remnant shocks are special because they've been known to be great accelerators of particles.
Yes.
Some of these galactic cosmic rays, for instance, yeah, exactly. So the galactic cosmic rays, for instance, they come from supernova shocks. At least to our understanding for now.
Canonically, yes.
At least to our understanding of now. I mean, there are of course other sources, but we will look at supernova shocks because they're non-relativistic. And when I mean non-relativistic, it's an actual limit because in the heliosphere we do have shocks, and shocks are ubiquitous in all systems. You can see them in many different places in space plasmas, in astrophysical plasmas, in galactic intergalactic plasmas, in many other places. So they come in all shapes and sizes. Um, and their fundamental characteristic is that they can heat the plasma and also accelerate a small subset of particles to very high energies.
Yep.
So when I say particles, this includes ions and electrons,
Good.
because we are in ionized gas. So people have tried to use the heliosphere, where we have so many different spacecraft. So, for instance, when you think about the space, like the space age, we've had hundreds of spacecrafts go into orbit and also see these shocks in reality. So people have tried to use these shocks to understand how shocks in other astrophysical systems would
Ah,
evolve.
right. Yes.
Um, so one such thing that astrophysical shocks. Okay, let me put it this. So one of the things that makes astrophysical shocks observable is the synchrotron emission.
Okay.
So it's from highly relativistic electrons, and they emit radio or X-ray radiation in of course in these wavelengths, and this is how we can even see these things, and this is how we even know that some of these galactic or cosmic objects can accelerate such high energy particles.
Yes.
And this is important because the synchrotron radiation is really well studied. It has a excellent theoretical background to it. So
Yes.
if you look at all my references there, some of them are really old, like for instance, Born, and some from the 40s and 30s onwards. So it's
Love
pretty
it.
amazing how long,
Love it.
yeah, how long some really famous people in there too. So
Oh yeah.
it's pretty amazing how synchrotron emission has been studied for so long. But the problem is with the heliospheric shock is that electrons cannot be accelerated to that high, or it's not the fact that they cannot, but we haven't observed them being accelerated to that high energies.
Okay.
So when I talk about high energies in supernova remnant shocks, they supernova remnant shocks can accelerate particles up to hundreds of TeVs. These are tera electron volt.
Yep.
This is 5-6 orders of magnitude higher than what we have seen in the heliosphere. So this presents a huge problem, right?
Indeed.
Um, so um, so what one of the missions has been of all these heliospheric missions is to find a shock which would be strong enough to accelerate at least to a certain order of magnitude where they would emit some radiation or show some characteristics of these supernova shocks.
Right.
And apparently, this is exactly what the Parker Solar Probe, when it got very close to the sun, saw. So it's very exciting. This is why I meant
Very.
that Parker Solar Probe has opened new gates for us in this sense, is because when it got really close, it saw two shocks, particularly. One of those shocks, it was called a Labor Day shock because it was very close to Labor Day.
Love it. I love
Very
it.
uncreative, I
Very
know.
good. Very good.
So it was on the 5th of September 2022.
Mhm.
So it was like observed really close to the sun. And when I say really close, I think it was like about 10 million kilometers from the sun when it
Yeah.
observed that shock.
Close enough.
It's pretty close on the cosmic scales.
Yes. Yes.
And the other shock was observed last year in 2023 in
Okay.
March on March 13th.
Okay.
And it was observed somewhere around 35 million kilometers or so.
Mm.
So yeah, so these two shocks, um, since they were observed really close to the sun, and something we have to understand about solar shocks is that they are driven shocks. So this means you have some sort of an eruption coming out of the sun.
Yep.
It drives a shock because it's flowing through a fluid medium, and it's going to drive a shock. And the stronger your eruption, the stronger your shock's going to be.
Ah,
And it also depends on the medium, of course. But these shocks, when we are talking about strong shocks, these are really fast and strong shocks. So, for instance, the 2023 March 13th shock was quite fast. It was almost 3,000 kilometers per second. It was
oh,
and it drove a shock. Yeah, it was quite strong,
yeah.
and it drove a shock which was really strong, and it was able to accelerate hundreds of MeV protons, and also up to 7 MeV electrons, or even higher, because our instrumentation is capable of measuring only up to 7 MeV.
7.
Yeah, we have a little cutoff there, so we don't really know how far it goes, but we are pretty certain that it accelerated up to 7 mega electron volts. So
Wow.
this is pretty exciting, because previously some of these Voyagers, when they observed really strong shocks. So this was back in the 80s, when we were in a solar maximum at that time. Some of the Voyager scientists found a really strong shock, which was able to accelerate up to 2 or 3 mega electron volts,
Cool.
which is pretty impressive. But that was pretty far from the sun,
Right.
and 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 this I will come to this a bit later, because when you go further away from the sun, the magnetic field, the solar magnetic field, also falls off,
Yes.
which makes the possibility of emitting synchrotron radiation very difficult. Let's say so. It's not. I wouldn't say it's not possible, but it's highly
Challenging.
improbable.
Right.
So um, so since we are very close to the sun, it's the ideal environment where you have very high magnetic fields, you have particles being accelerated to very high energies,
Okay.
and then you have a shock which is fast and strong enough to sustain this particle acceleration
Okay.
for quite a long time. So if you go to the first figure, I can already kind of
Sure.
show.
Let's go to figure 1. Let's take a look at what we got here. Okay. Now zoom in a little bit.
Yeah,
Here we
exactly. So
go. Okay.
here are the two radio spectrograms. Each one representing each shock, of course. So we have three different panels here. The first panel is what you call just the Stokes I. It's just the intensity parameter. So the radio spectrogram here, these are time frequency diagrams. So Parker Solar Probe measures about let's say 120 different frequency channels, and these are in time. You can make a spectrogram out of those. And I've made several markings here. So some of these markings are your usual solar radio emissions. So these come in 5 different types: type 1 to type 5,
Okay.
very non-creative again.
Yeah.
So I marked here type 2 and type 3 radio emissions.
Uh,
So type 3
yes.
radio emissions are these like really intense emissions which come out of the
Burst.
sun during solar flares. And then you
Yeah.
have the type 2. Those are these fragmented, kind of intense, but still fragmented emission.
Yeah.
Um,
Okay.
so those are also from shock waves, but there are some differences here. So synchrotron emission and the difference between synchrotron emission and these emissions is that synchrotron emission is incoherent. That means
Yes.
it's emitted by individual electrons. So the emission comes from individual electrons, while type 3, type 2, all these are coherent emissions, which
Okay.
are emitted by collective processes. So collective plasma instabilities, for instance. So that means their intensity can be really high. While synchrotrons,
Yeah.
since there's quite a lot of limitations to single electron emissions, they cannot really be that
Intensity.
high intensity in the radio spectrogram, at least.
Yeah.
So this is what we see here. So the synchrotron emission here, I marked three different emission lanes, let's call them,
Okay.
of synchrotron emission for the September 5th, 2022 shockwave.
Okay.
And you can see them on the spectrogram as well. And we made three different fits to see how they actually align with how the shock is moving.
Okay. Okay.
And for the second shock on the March 13th, 2023, you see there's only a single synchrotron emission lane,
Yeah.
and it's very dim. So we've also marked them with some markers there, and you see the typical type 2 and the type 3 radio emissions there as well. And I've also marked there this FPE, which is the plasma frequency, which is on the
There we go. Yep. Around.
exactly with an arrow. The plasma frequency is important because it forms like this. It's a screen beyond which you cannot have electromagnetic radiation. So it's a local plasma frequency. So even if there are non-local emissions coming to you at even lower frequencies, they will not make it to you because they are evanescent past this plasma frequency locally.
Yes.
So now to give a nice ideal view of what synchrotron emission is and how they are actually formed. So you do remember I said like you need very high magnetic fields and also high energy electrons. So high energy electrons, I mean relativistic electrons. Since these are single electrons emitting, you would need them to be so it's ideal to use Lorentz factors. So you want them to have Lorentz factors greater than 2, ideally. So if the magnetic field is really high, then Lorentz factor, smaller Lorentz factor electrons with smaller Lorentz factors can emit synchrotron radiation.
Yes.
But if the magnetic field gets weaker, and as the magnetic field gets weaker and weaker, you would only get emission from the higher Lorentz factor electrons.
Yes, because there'll be a distribution there.
Exactly. So you need a distribution of electrons.
Yes.
So synchrotron emission comes from electrons gyrating around these magnetic fields. So exactly. So they're gyrating around the magnetic field, and since these are relativistic electrons, so you can think of them as cyclotrons.
Oh yeah.
So cyclotrons are just non-relativistic synchrotron. So, or rather, the synchrotron is relativistic cyclotron.
In other words, yes.
So these electrons, they're gyrating around the magnetic field, and they. Oop,
I'm good.
So these electrons, when they are at a certain pitch angle, or the angle between the magnetic field and the electron gyration, they can emit a breaking radiation, which comes out as, of course, a particular emission, and this emission can be beamed if it is in the relativistic form. So because when you have relativistic effects put into it, you get time dilation and length contraction and all these things. So your electrons radiation, the electron emits, gets beamed. So this beaming is really important because synchrotron emission is highly beamed emission.
Yes.
So that means you have a factor of 1 over gamma, which is the angle at which it beams. So the higher the electron's energy, the more beamed it is.
Yes.
So the higher the Lorentz factor, the more beam. So that means you will only see, like, these are like lighthouse sort of emissions. So as the electron moves past, you see this lighthouse sort of emission going past. So this is an important factor of synchrotron. So these are single electron emissions, but you don't have a single electron in any source. You have multiple electrons, or you have like a distribution of electrons. And so when you have a power law distribution, let's say, when you have a power law distribution of electrons, you would get a spectrum of synchrotron emission.
Yes.
So the spectrum of synchrotron emission, it can be really well characterized in a spectrogram, ideally. So something what we have here in our figures. So they are characterized in a spectrogram by so they're bandwidth. For when I mean bandwidth, that is the extent. So the highest frequency and the lowest frequency at which they can be observed, it is 100% in relative bandwidth terms. So when you normalize them by the central frequency, it's 100%. So that means they're quite broadband emissions.
Yes.
So this is quite important because it
Where?
distinguishes them from the other two emissions that I've also marked here, these type 2 and type 3 emissions.
Mm-hmm.
And the second characteristic is that if you notice immediately, compared to the other type 3 and type 2 emissions, synchrotron emissions are very diffuse. You see them as like light, diffuse emissions in the back, broadband and diffuse. So
Okay.
this is how you would characterize synchrotron emission,
Cool.
at least on the spectrogram.
All right.
And this is exactly what we have done. The first thing we did was to characterize their morphology on the spectrogram,
Okay.
which is that they're diffuse and broadband. And
Okay.
all three synchrotron lanes here are
Yes.
100%. They all have 100% bandwidth, and they are all diffuse. And it's the
Okay.
same case for the second shock as well,
Okay.
which I have named S1 and S2. Very uncreative again.
Yeah. Gotta work on your naming
um,
there.
Exactly. Um, so um, so these are quite important distinctions. And the third distinction is something we call brightness temperature.
Yes.
So the brightness temperature, so what you see plotted here in units is the solar flux units. So this is intensity units. So you can see them in the description of the figure as well. So 1 SFU would be something like 10 to the power minus 22
Yeah.
watt per meter squared hertz.
Right.
So, but these are not corrected, let's say, for the solid
Okay.
angle. So,
Okay.
but if you want to know exactly what the brightness of this particular emission at the source was,
Yes.
you need to find the temperature of the electrons themselves,
Yes.
it's called the brightness temperature. So maybe we can go to the second appendix. I have a
Sure.
short
Let's
text
do
there,
it.
and also some figures there, which will help us
Let's
understand this
go to
a bit
Appendix
better.
B, which is transverse E and M wave properties. And
Um, and I think it's appendix C.
C, sorry. Appendix C, brightness temperature.
Sorry.
Yes, here we go.
Yeah,
Okay.
brightness
And
temperature.
those of you,
So
reminder, brightness temperature.
exactly.
That's T. TB
So
is,
yeah, TB is the brightness temperature,
yes,
so it
yes, yes.
follows the Rayleigh-Jeans limit.
Okay.
Um, so ideally, what you would want incoherent emissions to be is that they would have the same temperature as the emitting electrons.
Okay. So
So the emitting
TB
electrons,
or TE. Mm-hmm.
exactly. So the emitting electrons, let's say they can have 10 to the power 10 Kelvin temperatures,
Okay.
which is very high temperatures.
Indeed.
So they're highly non-thermal. Um, so that means the emission which comes out of them should also be of the same level. So that means the brightness temperature should give us the actual temperature of the electron. So
Okay.
this is the black body radiation stuff.
Correct.
So
Yes.
so if you have the brightness temperature, so at the source you can find what the so there is a certain limit beyond which you cannot have the brightness temperatures to exceed. So one of these limits is called a Compton catastrophe.
Yes.
So I have this limit here. So what this is that so we know what Compton scattering is, but this is inverse Compton scattering. So when you have exactly so when you have inverse Compton scattering, this means the electrons actually take energy from the photons themselves.
Yes.
So this happens quite a lot when you exceed the Compton scattering limit, which is set by 10 to the power 12 Kelvin.
Mhm.
However, this is for 1 GHz. So what we found was that for the frequencies that we observed in around 100 kilohertz, this becomes much higher.
Yeah.
So the temperature becomes 10 to the power 13 Kelvin, as you would see there. Uh,
Yes.
because of water.
Yes. Okay. Okay. I'm with you. I'm with you. Mm-hmm.
So yeah, so since it exceeds this, we can actually okay. So there's the figure 6. So we
Yeah.
plotted all three synchrotron emission lanes for the first
Yes.
shock in the
Yes.
first
On figure one.
top panel.
Uh-huh.
And if you see, I've also marked there the TB limit, the inverse Compton limit, which is 1.3 10 to the power 13. Yeah, for the top one, and
Or
for the
top
bottom
one.
one, it's 1.7.
I'm with you.
So this gives us some very important information because the
Hmm.
top, in case of the top one, you
Yeah.
would see that we don't even see the limit. We are well below the limit. So we are an
Right.
order of magnitude. As a matter of fact, we are an order of magnitude, or nearly two orders of magnitude below the limit of the inverse Compton scattering.
Okay.
So this tells us that this tells us two things. Either the electrons are not that dense, let's say. So you don't have a high
Okay.
density of electrons
Yeah.
because
Number
the
density.
flux of
Sure.
electrons, so the number density is probably low,
Okay. Okay.
or
Sure.
the
Perspective.
emission is not coming towards you. It's not beamed towards you.
Right. Right. Right.
So there are two things. So it's not directly beamed, and it's maybe we are only seeing like some side lobes of the emission.
Yes.
Um, in the case of the second one, if you look, like there's a clear pattern. It keeps increasing towards the arrival of the shock at the spacecraft.
Yeah.
So
Okay.
there's a clear exponential kind of an increase as the shock comes closer and closer to the spacecraft.
Got it.
And and when you come very close to the spacecraft, and when the shock comes very close to the spacecraft, it even exceeds the limit set by the
Yes.
inverse Compton scattering. So that's the theoretical limit which we are exceeding. So here I need to mention something about the theoretical limit. It
Yeah.
is that it's calculated for 2 pi steradians. So it's not really calculated for 4 pi, which means you're inside the source itself.
Yes.
Because 2 pi steradians means you're seeing the source coming from somewhere else towards you.
Yes.
But when you're inside the source itself, you are fully isotropized. So you are getting emission from all directions, which
Yes.
increases the limits. I mean, the limit kind of
Fair enough.
falls apart. There,
Yes.
we have to recalculate the limit.
Fair enough.
So this kind of gives us the impression. So this gives us another confirmation that these are synchrotron emissions. That these are the characteristics, and everything follows the characteristics of synchrotron emissions so far.
Cool.
And if we go back to the original text now,
Yeah.
to
Let's
the,
go. And I want to make or my comment, I guess. And that would be we have two
Mhm,
arrows here at the top on the September 5 in red and then the 13th in blue.
exactly,
And so this is
the arrival of the shock. So, okay,
a yes.
thank you for pointing it out
Yes.
because I did
Well,
talk
because you
about the
mentioned it in
arrival
the
of the
previous figure. I was going, oh, that must be what that is in that figure. Yes.
exactly. Yeah, I just realized I didn't mention that important detail because that
Okay.
is the arrival of the shock. So one of the
Yes.
important things here is that not only is Parker Solar Probe observing these shocks remotely, it's also observing them in situ.
Yes.
That is the most unique thing here, is that we are able to observe synchrotron emitting shocks in situ. This allows us to make this direct bridge with astrophysical shocks.
Very cool.
So,
Very cool.
so in the next panels, then we come to the polarization details.
Yes.
So
So,
this,
uh-huh.
yeah, so the polarization is another important detail of synchrotron emission. Synchrotron emission is not like plasma emission, which is you have type 2 and type 3 radiation,
Mhm.
which is polarized usually in the ordinary mode. So think about plasma waves or electromagnetic waves in highly magnetized plasma. And in the near sun medium or in the solar wind, it's a highly magnetized plasma. It's fully
Yes.
ionized and highly magnetized. Um, the thing about this kind of a medium is that your electromagnetic waves don't propagate only along the magnetic field, or they they don't just propagate as a single mode, but they propagate as two different modes in highly magnetized plasma. It's the ordinary
Yeah.
mode and the extraordinary
Yeah.
modes.
Okay. Okay.
And
Yes.
when you have and then when you have a turbulent plasma, or a plasma which is highly, let's say, I wouldn't just call it turbulent, but
Tangled. Yeah.
coupled plasma,
Yes.
a coupled plasma, then you would have both these modes propagating together. it's an important concept which was developed
Yeah. Okay.
in during the early days of plasma physics. But the thing is that
Yeah.
we consider something called the cold plasma. So we will only in this limit you can have waves in certain modes.
Hmm.
So for plasma emission, the modes have always been the ordinary mode because it's emitted close to the plasma frequency, while and also they're emitted by electrostatic waves. That's another detail. While for synchrotron emissions, since the electron emits along the perpendicular to the magnetic field or along its velocity direction, which is perpendicular to the magnetic field,
Uh-huh.
it it comes off as as the extraordinary mode.
Mm.
So this is an important detail. So synchrotron emission comes off as extraordinary mode, especially in the optically thin part of the spectrum.
Okay. Yes.
So another detail about synchrotron radiation is that it has an optically thin part and a thick part. I didn't mention this before because we are interested mostly in the optically thin part of the
Mm.
spectrum, which is the high energy part of the spectrum.
Right.
There's a cutoff which forms the optically thick part.
Uh-huh.
In the optically thick part, people do consider the O mode to be present, but in the
Okay.
optically thin part, it's usually just the X mode, which is the
Okay.
extraordinary mode.
Okay. Okay. I'm with you.
And synchrotron emission should be polarized. If we follow theory, it should be polarized to very high degrees,
Yes.
and also
Very.
it should be plane polarized. So it's not circularly polarized, but
Right.
yeah. So it's polarized. If you go down to the polarization section,
Let's slide
we
down
can
a
talk
little
a little.
bit. And we got a
It should
polarization.
be, yep, exactly here. Um,
Did I lose it?
it's a bit about, I think
Did I lose it?
it was chapter 2 or section 2.3.
2.3. Because we're
Yeah,
in.
that's the one.
Oh, here we go.
2.2, sorry, depolarized.
2.
Yeah,
Oh, okay.
so here we do
Yes.
notice that our emissions are polarized in a certain way. So the best way to understand polarization in a magnet in an active plasma is
Okay.
using the Stokes parameters.
Yes.
Um, so when you have the Stokes parameters, so you have four different Stokes parameters. So you have I,
Hmm.
Q, U, and V. So these can be found in several different original papers, which
Classic
have
text.
like started classic texts, and also you can even go back to Stokes himself, the text of Stokes himself to read
Hmm.
about it. It's very interesting history because
It
this is
is.
where
Yeah.
plasma physics and optics came about. Mm, so we are interested in circular polarization here because plane polarization is usually canceled out due to any sort of Faraday effect or any sort of turbulence at very small scales. So we are interested mostly here on the circular polarization. So
Great.
there's a interesting way to get the circular polarization, which is so circular polarization, as it said in the text there, it's a oh my God. So it's a difference
Okay.
between the X and the O modes.
Yes.
Basically, the intensity of the
Intensity.
X and the O modes, and it will give you how how the polarization vector, the electric field vector, rotates around the magnetic field. So
Okay.
this is what we want to know,
Mm.
and how the electric field and the magnetic field rotate with respect to each other. And this should
Yes.
be in a certain way. I mean, the expected polarization should be, as I mentioned, the plane polarization should be quite high, about 80% polarized
Okay.
for synchrotron emission. For electrons of this energy range, let's say,
Mhm.
um, but when you go to the lower energy range of synchrotron emission, you start seeing circular polarization more and more. And it happens to be that circular polarization, you remember the beaming part of synchrotron emission, I said.
With the yeah, yeah.
So when you observe it directly in the middle of the beamed electron, or the beamed radiation. Exactly. If you view it that way, it will always be plane polarized.
Yes.
So it should be plane polarized. But when you go a little bit at an angle to the beaming, you start seeing a little bit of the circular polarized
This
bits.
is cool. Okay. Okay. This is cool. I'm
So
with
that's
you. Yep.
because, yeah,
Yep.
so the electron is
Okay.
rotating like this and it's emitting at a certain range. So when you look at it from below, it starts to look like it's elliptically polarized. It's not
Right.
completely circular polarized, it's elliptically polarized.
Okay.
So it's very small degrees of circular polarization.
Uh-huh.
And this is exactly what we see here for the first shock. So when we go back to the first
Figure
image
one. Yep. Yep.
in figure one, in the
Yep.
second panels,
Right. Right here. Mm-hmm. Yep. I'm with you.
in the second panel, you see some bits of blue in the spectrogram
Jokes. Mm-hmm.
itself. A bit of blue, indeed. So those are from circular polarized parts of the synchrotron emission that's arriving at us. So when we measure the level of the level of polarization, we find here it's about 15 to 20%. And apparently, there's a nice little way you can estimate the electron energy without even knowing the electron distribution from just the polarization, which
Cool.
is to use, as I said, it's at an angle. You start to see the circular polarization. So the angle, the synchrotron emission beaming angle, is given as 1/gamma.
Gamma.
So
Yeah.
when we use that, and when we use the level of circular polarization against it, you usually get the electron's energy, the
Yeah.
gamma
You can back
factor.
that out to get the energy. Okay. I'm with you. Yep.
Exactly. And when we use that to find the electron energy, we found it should be between 4 or 6 mega electron volt.
Okay.
And
Good.
this was very interesting because this gives us a way of cross-checking with our electron observations as well, which I'll come to next. And one more property of the radiation. You remember I said it should be extraordinary mode, polarized in the
Yep.
extraordinary mode.
Yes. Excellent.
So which means so when the magnetic so using the magnetic field, we can actually check if the emitted radiation is in the ordinary mode or extraordinary mode.
Yeah.
So, so when the magnetic field is pointed inwards, the polarization would be exactly. So it should be in the ordinary mode. So here the magnetic field is pointed inwards, which should mean that your BR is negative. That means
Yes.
the polarization should be in the ordinary mode. But
Yes.
however, we see extraordinary mode polarization because our polarization is on the
Okay.
blue side here. So
Okay.
this tells us that the polarization is in the extraordinary mode as well. So this gives us another confirmation that this is not plasma emission, but this is rather synchrotron
Synchrotron
emission.
emission.
And this
Yes.
is purely synchrotron emission, and it is not it's not convoluted by anything else,
Cool.
which is
Very
an
cool.
important detail because
Yeah.
a little bit of a tangent here because synchrotron emission has has been seen before or has been um, let's say has been suggested before for some of the radiation that we see from interplanetary shocks.
Okay.
Maybe not interplanetary, but very close to the sun.
Mhm.
But there was no way to really identify it because we wouldn't really know if this was synchrotron emission
Nice.
without getting close to it and measuring the actual emission itself.
And here we are.
Oh, here we are,
Here we
exactly.
are. We're close. We're measuring
And we did
it.
not have polarization either back then. So
Cool.
this has proven to be an excellent endeavor with Parker Solar Probe.
Yeah.
So yeah, this is about the polarization. So now we have three different confirmations, if you think about it. One is through the morphological sense. One is diffuse, and the bandwidth is 100% self-absorbed synchrotron bandwidth, which is 100% emission. And the second one is the brightness temperature. And
Yes.
we found that the brightness temperature also is below the inverse Compton limit, which is very important to identify synchrotron radiation because it
Yes.
cannot exceed the inverse Compton
Oh,
limit.
but that.
Um, and the third one is the polarization of the emission itself. So we
Yeah.
have three different identification methods used here to confirm that it is a synchrotron emission.
Synchrotron. That's very
And
cool.
now finally, we can go to the electron. So this is the last section of the paper, which is 2.4.
Let's go down.
Last section of the results, at least, because we have four results.
Go down to 2.4
Yeah,
distribution.
2.4.
And
Yeah, the distribution of electrons.
mm-hmm.
So what Parker Solar Probe also does is it of course measures everything in situ. So this means it
Yep.
also has a particle detector, which is called the integrated particle detector. So it's the
Mm-hmm.
ESIS instrument suite. And the how uh, how astrophysicists study synchrotron radiation, or what do they get out of synchrotron radiation
Oh,
of all these supernova shocks, is
yeah.
that they want to study the energetic particle environment at these
Yes.
shocks.
Yes.
So synchrotron emission allows us a direct way to identify what the electron distribution at the source is.
Yes.
So
That's very
this you can
important.
see that it's, yeah,
Uh-huh.
exactly. So this is very important because
Uh-huh.
we have a particular theory which is scale invariant, which can be
DSA.
used. It's one of the most widely used theories,
DSA.
and exactly DSA. So it's the diffusive shock acceleration theory, which can relate any different spectra. So it should be the same across any medium as long as you have the conditions necessary for it. So what DSA predicts, so DSA is an acceleration theory, so it's a diffusive shock acceleration. So
Yep.
when you have a shock, what it says is that, so this was put forth by Fermi,
Yes.
Enrico Fermi,
Yes.
originally in the 1950s. And what he suggested was that, so he was very involved in the cosmic ray problem. So his idea is like, so how are these cosmic rays around? Like, I mean, like, how do they
Accelerator.
get accelerated to such high energies?
Right.
And Fermi suggested that it must be some mirroring process. So if you have like some moving molecular clouds, the particle can bounce off of each other, gain energy. So
Yes.
it's like a tennis racket. So when it's
Bang,
like
bang,
you
bang, bang,
playing
bang, bang,
tennis.
bang, bang,
So
bang.
exactly. So when you have a shock, this is exactly what a shock does. So when you have two converging flows, you can have particles reflect off of each other and gain energy every time they cross the shock.
Yes. Mm-hmm.
And so
Good.
DSA is exactly what you would think immediately is it's a preferential acceleration method. So it would form a power law naturally.
Yes.
A power
Right.
law is a very preferential, like a distribution. It's a it's preferential acceleration. So it's not heating, but it's acceleration. So only a few particles can go through DSA,
Yes.
and so it produces a power law. And this power law is it extends to several orders of magnitude. It's even called the Great Power Law in the sky. So for cosmic rays, because cosmic rays extend for tens of orders of
I
magnitude,
don't
so
think
it's
I've ever
just
heard
pretty
that
amazing.
before. Okay, very good.
So you can apply the same to electrons as well. Of
Sure.
course, electrons through observation. So what people have identified is that the spectral index that you retrieve from synchrotron emissions from the
Okay.
photons that you receive
Okay.
can be converted to um, uh, to 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 the particle power law as well. So what
Yes.
is the power law of the emitting electron? And this is given through this relation. Alpha is similar to delta minus one over two
Yes.
here.
Uh-huh. Mm-hmm.
So alpha here is the spectral index of the synchrotron photons, and
Mm-hmm.
then delta is the spectral index of the emitting electrons at the
Yes.
source. So this is how astrophysics physicists have always tried to identify what is the spectrum of the emitting particles at their supernova remnant or at the AGN jet or pulsar nebula, whatever.
Good. Very good.
So they use this for everything.
Yes.
So if this is the case, we should find some match with it as well. So we should be able to use our synchrotron spectra, and we should be able to find the electrons, the spectrum of the electrons.
Yes.
And since Parker Solar Probe is measuring the shock in situ, it can also measure the electrons. So it can get also direct measurements of
Cool.
the electrons by itself
Cool.
without even converting it from the photons. But
Right.
what it allows us is to identify if the theory stands and
Correct.
if it is indeed applicable
Yes.
without any losses and such.
Yes. Very
So
good.
it also gives us a chance to double check DSA theory. So what kind of emission mechanisms? So what are the conditions for acceleration of such particles? And also, what is the conditions under which such radiation is also emitted
Good.
with the same power law index as the
Very cool.
electrons?
Very good.
So this is exactly what we set out to do. And first, for this, we needed to get an estimated power law for the photons or the electrons
Okay.
from predictions, from shock predictions. So DSA is a very elegant theory. All it needs is the compression ratio at a particular shock to
Uh-huh.
give you what is the spectrum of the particles which come out of it. So when we look at the two shocks that we were talking about, the first shock is the September 5th shock. It's a quasi-perpendicular shock. So this is a good diagram here to show. So the first shock is the September 5th one, S1. It is a
Mm-hmm.
quasi-perpendicular shock. So PSP is this little cute spacecraft there,
Yeah.
looking at the shock, which is in purple, and you have the magnetic field lines coming out in blue.
Okay.
And
Uh-huh.
I also drawn the angle between the shock normal and the magnetic field. So they're Q
Yes.
parallel and Q perpendicular.
Yes.
So the September 5th shock was quasi-perpendicular, at least the one which came towards Parker's solar probe was quasi-perpendicular.
Mm-hmm.
And it gives us certain limitations, which I'll talk about in a
Yeah.
second.
Right.
And the compression ratio of this particular shock wave was about 2.5, which
Okay.
is when I mean compression ratio, it is the difference. It is a ratio between the upstream and the downstream. Exactly, downstream densities.
Good.
And this was about 2.5 for this for the first shock. And for the second shock, it was quasi-parallel. It was coming
Yeah.
directly. It was somewhere around the apex of the shock, and
Nice.
the shock was quasi-parallel.
Okay.
And here the compression ratio was 4. So
Okay.
4 is the limit for compression ratios.
Yes.
4 would
For
mean
ultra.
it's a strong shock.
Yes. I'm with
It's a
you.
strong shock limit,
Mm-hmm.
especially for a monoatomic gas such as the solvent. So
Yes.
um, this is an important distinction. So one is a quasi-parallel shock, and the other one is a quasi-perpendicular shock, and one has a compression ratio a little bit lower than a strong shock, and the other one has a full strong shock compression ratio.
Cool. Okay.
Um,
Okay.
and so the compression ratio, as I said, DSA can give you the expected spectral index
In that. Yes.
for the compression ratio you have. So
Mm-hmm.
apparently for 2.5, the spectral index would be somewhere around 3. The expected electron spectral index, the distribution of the electrons should have a power law spectral exponent of about 3. And for the for the March shock, for the S2, since it's a strong shock, it has a compression ratio of 4. You would expect a power law index for the electrons of 2, which is the limit of DSA.
Good.
And this is important because, as I mentioned, you can convert these to photons, right? So
Yeah.
the
Yeah.
photons should then have. So, for instance, for the strong shock, the March shock, exactly for the March shock, you should have a photon spectral index of 0.5. So very flat spectrum. And then for the September shock, the one on the right here,
Yes.
you should have a photon spectral index of about 1.
Okay. Good.
So double that of what you would see in the March shock.
Yeah.
So this is the expectation.
Parallel one.
So
Okay.
is it the reality? So if we go to
We should
exactly,
measure
so
that. We should measure that.
and apparently Parker Solar Probe can measure this,
Very
and
cool.
it did. So if we go to Figure 3, we will find out
Oh, very good.
if
Okay.
our
I'm going to zoom out a little bit to get them all, and I'll zoom in.
exactly it's a bigger figure.
Okay.
Um,
Okay.
So in panel A, we have the
Really
full
good.
time series of the particle measurements. So this is in counts per second. So it's not
Mm-hmm.
necessarily intensity units, but
Yes.
it's counts.
Mm-hmm.
But the shock is again identified by the arrow on top.
Yeah.
And you can also see all the energy channels that are being plotted here. So you have from 0.7 MeV up to 3.4 MeV.
Mm-hmm.
So these are relativistic electrons. So from mildly relativistic to actually relativistic electrons.
Cool.
Um,
Okay.
and as you will note immediately from the counts from the time series, you don't see so many of these electrons very far away from the shock. But when the shock arrives, you see quite a lot of these electrons arriving. You
Yes.
have like a bump in the electron counts.
Mm-hmm.
Um, and when we convert this to intensity units,
Okay.
we find, so that is panel B. So when
Right.
we convert this to intensity units and when we combine this with the low energy electrons as well, which are in blue,
Yes.
there, the blue dots,
Yeah.
you can actually fit a line. So here in the x-axis, you have the energy, and the y-axis, you have the intensity. So the intensity is given in particles per centimeter squared,
There.
per seconds, to radians per keV. So it's in keV units as well.
Uh-huh.
So these are highly intense particle
Cool.
fluxes. So you would notice that um, there is quite well. So there
Yes.
are two instruments being combined here, or three instruments rather. So you have EPI-low, which is the low energy detector.
Okay.
You can see it up to 200 keV,
Mm-hmm.
and that one connects nicely with EPI-high. Het A and Het B are two different viewing directions of the same detector.
Okay.
So
Good.
one views, so Het A views along the sunward direction, while Het B views along the anti-sunward direction.
Okay. Ah,
So
both.
when I say anti-sunward, so that means if the spacecraft is moving this way toward, so this is the sun, and the spacecraft is moving like this, and the
Okay.
magnetic fields are coming out like this,
I'm with you.
the 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 spacecraft actually measures along the magnetic field, but it measures in two directions. So A looks at the sun, while B looks at the other way.
I
So
guess.
basically, in pitch angles, this would be 0 degree pitch angle and 180-degree pitch angle.
Okay. Zero pi.
So if the magnetic field is pointed outwards, of
Uh-huh.
course.
Uh-huh. Uh-huh. Well, yes. Okay.
So what we see here immediately is that there is some anisotropy
Mm-hmm.
because they don't have the same fluxes. So the red points or the orange points are from Het A, while Het B has green points. So there is some anisotropy here.
Uh-huh. There's a little variance there. Yes.
So exactly. So there's a
Um,
variance in
7.
the intensity at each energy.
Okay.
Their
Yeah.
power law exponents are pretty much the same, very close to each other given the error bars, but
Fair.
the the anisotropy prevails.
Uh-huh.
So this raises some important questions because the anisotropy DSA, if it is active, you would see highly isotropic fluxes of particles. So that means you should see same amount of particle fluxes from any direction. They're highly isotropic. This is because DSA works on pitch angle scattering.
Yes.
This means in pitch angle space, the DSA isotropizes the particle pitch angles basically.
Uh-huh.
So when you have a bunch of particles coming in, they get scattered. So DSA would scatter them in a way that they would have the same pitch angles,
Yes.
or they would have all like different pitch angles, but they would have the same fluxes along all pitch angles.
Yes.
But we don't see that here. So this means
Oh.
this kind of gives us a hint that
Something's
DSA may
going on.
not be so efficient here. It might be
Okay.
active, but it's not really active. Active,
Yeah.
active.
It hasn't homogenized isotropic
Exactly.
enough.
So it hasn't it hasn't reached steady state or something like
Oh,
that.
that's fair. Okay.
So yeah, it's just not efficient. Let's just call it that. So here the other thing is
Okay.
that so we have two different spectral indices here for the fits. For the low energy up to about 1 MeV, our fit is about minus 2.85 in energy.
Yes.
While beyond that, there's a break, and we
Yeah.
see the spectral index breaks off to much
Steeper.
steeper, so minus 4.5 and above,
Yes.
which
Thereabouts.
is which is quite interesting because it could
Yeah.
be a break of energy, so there could be a rollover, or it could just be another population of electrons there
Yeah,
with a much steeper index.
yeah, that was my
Now,
guess.
to compare this with the photons.
Okay,
So what
okay.
we've done is we made slices at different times in the radio spectrogram, which I showed you which we saw in Figure 1.
Yes,
So we made different slices, so time slices
okay.
across several different frequencies.
Got it.
We made time slices at 1639 up to 1726,
Okay,
up to the arrival of the shock.
right.
And we
Yeah.
see three different lanes as we are supposed to see for this shock because there are three different synchrotron lanes. And we notice that away from the shock, the emission has a spectral index, a photon spectral index, which is about -3
Yes,
or -2 in some cases.
yes.
And as we get closer and closer, the spectral index steepens
Deepens.
to -8.
Yeah,
Exactly. So it
yeah,
steepens to -8. So
yeah.
this is interesting because this is interesting for two reasons. Because you remember the effect of the plasma frequency I told you,
Yes,
which is that when you get closer to the plasma frequency, much of your emission is absorbed
yes. Hmm.
by the plasma. So only the higher frequency emission is still observed. So
Yeah,
this means your higher your at higher frequency you have higher energy electrons emitting. So the higher energy electrons have a very steep spectral index
yes, yeah.
here in the electron spectra. So this means you're at these frequencies, you're either at the cutoff energy of the electrons,
Uh,
or you are only observing the very steep part of the energy spectrum. It's
right.
one or two, either one of that.
Cool.
But when we are further away, we start seeing this -3 and -2 actually has a perfect fit with what we see here with the electron energy spectra.
Mm-hmm.
So further away from the shock, we do have good corroboration with the electron spectra as well. But closer to the shock, of course, it's very difficult because we don't measure these high energies here. It might be very steep, or it's just a rollover.
Right.
But for the second shock, if we go to the fourth figure, we will see the second shock.
Just to be
The
clear,
same
this
thing
was
for the
for
second shock.
S1, so this will be S2.
Exactly.
Up, S2, there we go. Okay, zoom out a little bit.
For S2, we have the same
Yeah.
thing. I put an arrow down there to show where the shock arrives.
Mm-hmm.
And we have much higher energy channels here. So we go from 0.4 MeV up to 6.7 MeV. So that's about
Mm.
3 MeV higher than the previous shock.
Yes. Uh-huh.
And as you will notice, immediately the difference is quite interesting. Um,
Indeed.
the difference is that you have continuous fluxes of electrons coming in, unlike the previous case where you just had an increase at the shock. Here you have
Yes.
increases much ahead of the shock,
Indeed.
and you see that the increase keeps going. And when the shock arrives, you have this increase even like you have this exponential increase towards the shock, which is important because the shock is, of course, the one which is modulating these populations according to DSA. And by DSA, by DSA, which is this is a strong shock, we should expect an electron spectral index of -2,
There about. Yep.
um,
Yes.
which we actually don't. We actually see a steeper index at the low energies,
Yep. 268.
and at the high energies, it's a bit steeper as well.
418.
But something of note immediately is that there is isotropy. There is no anisotropy. The one we saw in the previous case, where
Yes.
you het A and het B saw very different fluxes, here they both see the same amount of fluxes.
Same. Yes. Yes.
And also, we are at much higher energies, which means that this low energy spectrum of epi low comes all the way up to two mega electron volt before
Yeah.
breaking,
Yeah. Right about
or
there.
even higher, or even a little higher. But But let's just say it's a
Okay.
2 mega electron volt,
Yeah,
and
there's
after that, it breaks up to a steeper spectral index of minus 4.1,
yes.
4.18.
I'm with you.
So how does this compare with the photons?
Yeah.
Now, if we do the same comparison
Uh-huh.
with the photons here on the right in panel C,
Yes.
we notice that ahead of the shock, an hour before the shock arrival,
Mm-hmm.
the spectral index of the photons is about -3, which
Three.
fits quite well, reasonably well, with the high energy part of the electron spectrum,
Yeah.
which is quite good. But as the shock comes closer and closer, we again see the steepening of the photon spectrum.
Yes.
So
Yeah.
this steepening is because of the plasma frequency again. So as the magnetic field falls, the plasma density doesn't fall as fast, but it still falls off as well
Yeah.
away from the sun. So this means the plasma frequency doesn't fall off faster than the magnetic field. So
Good.
it's actually slower than the magnetic field fall off. So
Yeah.
this means emission must be from higher and higher energy electrons as we go further and further away from the sun.
Yeah.
So this would automatically steepen the spectra. So this is exactly what we see here. We see the steepening of the spectra as we go further and further away from the sun,
That's another way to look
as
at
the
it. Yeah,
shock
yeah,
moves
yeah.
away further and further away from the sun.
Right.
Exactly. So this part of the spectrum, it could be from this f to the power -8, could be emitted by electrons somewhere in the tail end of the electron distribution, which we may not be seeing here.
Yeah, right. Because
Or
we
it
know
could
the
just
70.
Exactly. So it could just be, or it could just be the rollover or the spectral rollover, the exponential rollover of the electron spectrum itself.
Okay.
So, so these are the two options that we have given in the text as well. So, but the important thing of note here is that we found very good corroboration between these two different data sets. One is a remote sensing data set, and the other one is an in situ data set.
Yes.
And both of these are they match each other, like they match predictions from each other.
Good.
So you can
Good.
use one to predict the other, and this is exactly what we have found to be. They are well aligned, these two predictions,
Nice.
and this is quite
Consistency is
positive.
good.
Yeah, which is a really good thing, right? Because when you
Yeah.
have a theory, you want to put it to test, and if you can prove this theory, it's a good thing. So this is exactly what we have done, and we made some conclusions based on this because this
Yeah.
has some ramifications for what we observe in astrophysics as well.
Mm-hmm.
So, for instance, in astrophysics, recent astrophysical studies with X-ray polarimetric studies, for instance, this
Oh,
is called XP, which is the X-ray polarimeter polarimetric experiment, which has been recently launched.
IXP. IXPE. Yeah, yeah.
Exactly, IXPE, which has been finding quite low polarization than what is expected on the X-ray side. So
Ooh,
they've been finding about 4 to 5% or sometimes 10%.
less?
Actually, the expected polarization from these synchrotron sources should be 50, 60, 70, 80%, very high.
Okay.
But why do we see only 5, 6% when
Gotcha.
you actually observe? So this is because the magnetic fields in these regions are highly turbulent.
Yes.
So turbulence, what it does is that it randomizes any phases. So when you have a photon with a particular k vector, a particular phase, it gets randomized when it goes through some magnetic field. And it can also couple with different modes. As I said, when it's a
Sure.
highly magnetized and coupled plasma, you would have O and X modes coupling with each other. So you could
Okay.
have a mix of both modes. So
Okay.
there's a
Yes.
lot of things
Yes.
which could
Yes.
depolarize your emission.
Yes.
And this is exactly why we probably see very low polarization. And this study is no different because in the case of first shock, which is a quasi-perpendicular shock,
Yes. Uh-huh.
and quasi-perpendicular shocks are known to not have very highly turbulent upstream magnetic fields because they don't create these streaming of waves or streaming of particles, which can also drive waves.
Go right.
Um,
Okay.
So quasi-perpendicular shocks are not very ideal environments for upstream turbulence. So this is one reason why DSA was also found to be rather weak in our quasi-perpendicular case. It was
Right.
isotropic. This means the electrons were simply not being scattered.
Yes.
So when the electrons are not being scattered, that means they don't have enough scattering points or scattering of the waves which can scatter them. They're just not there.
Yes.
That's why they are anisotropic.
Okay. Okay.
So
Got
this is an important distinction between the two shocks because the second shock we found no polarization. Our polarization was probably I wouldn't say no polarization, but it was about 1% or below, very
right.
small. So we couldn't
Right.
measure that with some confidence, so we didn't include it. But it's very low, and this is exactly what also astrophysicists find when they find highly energetic particles in some places. In let's take a supernova like SN1006, as I
Sure.
pointed here, which is a bilateral supernova, which is a perfect piece to study or a perfect object to study
Uh,
what geometry does to your particles,
and
because in SN1006 you have particles
okay.
or rather synchrotron emission, X-ray synchrotron emission is concentrated on the quasi-parallel side
Supernova remnant.
of the supernova remnant, while the quasi-perpendicular sides are relatively weak in emission. So they sometimes don't even have emission, which kind of tells you a lot because the quasi-parallel shocks are very good at accelerating particles. So they can because they can drive waves and turbulence by themselves, which means DSA is highly active. And this is
Right.
exactly what we also found. We have high fluxes of particles in the quasi-parallel shock, while the quasi-perpendicular shock had much lower fluxes as well.
Yes.
Because in one thing I might have not mentioned is that the intensity, or maybe I have, because when we were measuring the brightness temperature, I
Uh-huh.
mentioned that the fluxes in the first shock was very low, an order or two orders of magnitude below the inverse Compton scattering limit,
Uh-huh.
while in the case of the second shock, it
Right.
was almost at the inverse Compton scattering limit. So this kind of tells us already
Cool.
that the synchrotron emission at the second shock, at the quasi-parallel shock, was much stronger.
Yes.
And we actually find some alignment here with the electrons as well, because the electron intensities were also an order of magnitude higher
Higher.
for the quasi-parallel shock.
Stuff.
So this kind of aligns. Everything aligns qualitatively, at least, really well,
Good.
with the fact that quasi-parallel shocks are highly efficient in accelerating electrons to very high energies, and this is exactly what astrophysicists have been claiming that it should be the case for them to see such high energy particles and also photons from these part of the supernova remnants. And I think this is a beautiful confirmation of
Yes.
what they've been predicting from remote sensing of such cosmic objects. So here we have proved through in situ observations that what they have been saying are indeed correct, some of these theories. So,
Nice.
and this is one of those. Of course, we've experimentally verified this, both the polarization, the characteristics of the emission, and also the electron spectra. So
Yes.
we've experimentally verified three different things. I've actually noted down what the three main questions, what we studied, and we so to summarize it, what we studied and what we kind of I wouldn't say kind of, but we have
You
addressed
did.
is the first question. The first question is that are the characteristics of the synchrotron radiation as predicted by theory?
Yes.
If so, how is it different or relatable to astrophysical shocks? This
Yes.
is the first question, and we
Yes.
found that it is absolutely fully relatable to astrophysical shocks, and it is as expected by theory.
Cool.
But where we do see deviations is in the polarization, and that is also predicted by theory, which
Okay.
says that when you have highly fluctuating magnetic fields, your polarization amount should go down. And this is exactly what we see. Um,
Yes.
the second question is, how are the particles which emit this radiation distributed? Are their characteristics relatable to the photon emissions?
Yes.
And is it also relatable to astrophysical shocks? And this, we found that this is also true in the case of these shocks because they are both produced by DSA.
Yes.
And the third question is, what about the shock itself, though? So does the shock structure itself play a big role in the radiation properties? And we have indeed found this to be true
Yes.
because the quasi-parallel shock emits more radiation than the quasi-perpendicular shock,
Yes.
high fluxes of radiation. And this concludes what the paper is about. And you can
Very cool.
summarize it in these 3 points. Yeah.
Very cool. Beautiful. Beautiful work.
Thank you.
Daniel, I want to thank you so much for walking us through your very awesome article.
Thank you.
Yeah.
I would also, I would also mention that some of these things I mean, the appendix. I didn't call out the appendix, but there are more details in the appendix on everything I have mentioned. So that is also, if anyone is interested, they could also take a look at the appendix for more
Please do
details
keep.
on these analyses, experimental details, I would
Very
call them.
cool. Details are good. That's why we write articles, right? So very good.
Exactly.
So you kind of touched on it a little bit there, and let me push on it a little bit and ask, where do you think we go from here, given the published article, given our rapturous
Mhm.
successes here? Are there additional measurements to make? Are there additional acceleration theories to consider? And just sort of next steps, where do we go from here, given the published article?
The next step here would be to find more such emissions from interplanetary shocks because now that we've seen two such ones,
Okay.
I have been seeing more of them, even in older data. So
Mm-hmm.
what it actually gives us, so
Uh,
there are two different paths one could take. One is for the heliospheric community, and one is for the astrophysical community itself.
sure.
So to the first one, to the heliospheric community, it gives us a very powerful tool to remotely understand if a shock accelerated energetic particles or not. This
Mm-hmm.
has been a huge question. Everyone knows shocks accelerate particles, but SEPs, like solar energetic particles,
Yes.
so no one knows if they accelerate to such high energy. So if you have relativistic electrons, you should also have comparable levels of protons. So
Yes.
this is something we will look at in the
Cool.
future. And on the astrophysical side, this has opened a very nice, I would say, a unique opportunity to build a bridge which has been long since overdue. So it's something that we should look forward to. So how can we bridge these two different scales?
Yeah.
Because
Right.
supernova shocks are 6 orders of magnitude bigger.
Right.
So so we need to understand the physics in each. So now that we know that their radiation physics is the same, so there's an accompanying paper
Yeah, that was
where
really
we also said
yeah.
uh, so there's an accompanying paper where we also said where we studied this quasi-parallel shock in detail,
Uh-huh.
and we found that the structure of the quasi-parallel shock is exactly as predicted by theory,
Cool.
which
Very cool.
means that you should, because it's a high Mach number shock or a very strong shock. So if a strong shock is predicted by theory, that means all the strong supernova shocks should also follow the same theory. So we can relate these together. So
Very cool.
to each other. So this is the future of that part of the work.
Cool. And I think we saw a reference to that 2024 work toward the
Yeah,
end.
exactly.
So we'll put a link to that paper too in the description below the video. So very cool.
Yeah,
Uh,
thank you.
well, it'd be really nice to see to see these two directions develop over the next couple of years. It'd be very exciting. And thank you, Parker Solar Probe.
Yeah, thank you, Parker Solar Probe. I think it's opened so many different possibilities on this realm. Yeah.
Absolutely. Very cool. Very nice. Emmanuel, thank you so much once again.
Thank you, Frank, for this opportunity as well. I had a fun time talking to you. As much fun
I
as
had a
I
fun
did the
time
work
listening to
as
the
well. So
article. I learned something new. So, I learned something new. So that's great.
that's
And
awesome.
I hope this, everyone, I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye bye.
Bye bye.